I am so glad you're here for another episode of Mechanism Monday, where every Monday we write out the electron-pushing arrow mechanisms for different chemical transformations. In last week's video, I asked if you could solve the mechanism for this chemical transformation, so if you haven't had a chance, pause the video now and try it independently. And make sure you stick around to the end because I'll give you another mechanism to solve for next week's video. The product of this reaction is called cinnamaldehyde, which is responsible for the odor and the taste of cinnamon. And this reaction follows an Aldol condensation pathway that you probably learned about in organic chemistry. In fact, I have a video about it here, where the first step in these mechanisms is going to be the deprotonation of an alpha carbon hydrogen. So here is the alpha carbon, and that can be deprotonated because it is more acidic than most carbon-hydrogen bonds. And that deprotonation step occurs through the addition of sodium hydroxide, where this can come and act as a base and deprotonate this to form an enolate. And that enolate species gives rise to the next step, which will provide us with a nucleophilic carbon position. So the product of that transformation is again that enolate, where now we have generated a nucleophilic carbon at this alpha carbon position. So these pi electrons will come back down, and this double bond will come and attack the aldehyde and benzaldehyde, again kicking up these pi electrons to the oxygen. And that gives us our next intermediate, which is going to reform this carbon-oxygen double bond. And now we're going to have a negatively charged oxygen here and the rest of our arrow ring on this side. And importantly, when we deprotonated the alpha carbon hydrogen, we generated water. So now this water molecule can come and be deprotonated by our negatively charged oxygen atom at this position to produce a brand new alcohol at that position. So now we have generated this product where this oxygen is now an alcohol, and we still have our phenyl ring on this side. And here we regenerated that hydroxide, and we still have alpha carbon hydrogens, which will be susceptible to deprotonation. And in fact, following deprotonation, we can actually go through an intermediate where we are kicking off this hydroxide ion to regenerate it while we formed water here. And notice that that also generates our new carbon-to-carbon double bond, which is how we get our cinnamaldehyde final product. If you enjoyed this week's mechanism, make sure to give it a thumbs up below. For next week's video, I'd love to see if you could figure out the mechanism for this chemical transformation. Drop it as a comment down below if you have any ideas, and make sure that you're subscribed to the channel so that you never miss another Mechanism Monday. I'll see you next week.